So hello and welcome to my first session about the tutorials of the usage of incremental driver to perform element tests of soils with advanced and simple constitutive models. First point of today will be organizational, where I will provide you the link to my GitHub account where all information and all documents you need are provided. Thereby, it is session 1, the folder where we will perform the simulations and run the codes. Then there are some listings and manuals about incremental driver, which are very general and you don't really need if you follow all my tutorials. Nevertheless, for sake of completeness, you have them here. Then we will have the incremental driver tutorials and my README. The incremental driver tutorials.pdf tells you what you need to download in order to run the codes. So we will be running the codes with Visual Studio, with Intel compiler, and you have to download them from these links following this procedure. After downloading those files and installing the respective softwares, you may download the project in my GitHub account, where I also provided you with a VF project file, which is available there, and you don't need to create your own Fortran project, so that everything runs pretty much out of the box in Visual Studio once the required packages are installed. So this was the organizational point, where what we need or what you need in order to run the things I will run today. Then, if you open this VF project file, you will open and download it all other packages. It will look like this. Now, let me tell some words about incremental driver. So incremental driver is a program written by Andrzej Niemunis, who was my lecturer and professor, and I am very thankful to him for giving us this software, which serves for testing constitutive models. Incremental driver enables element tests and deals with homogeneous fields only. An example, no consolidation, no spatial change of stress, strain and state variables, as well as no spatial change of material constants and gradients of deformation are allowed for. Incremental driver calls a material a routine constitutive relation with the syntax of the user material subroutine of Abacus. So if we open here source files, we will have here incremental driver, which calls the umat, which is also the material subroutine in terms of Abacus. We'll search, for example, here for umat, and we'll see here called umat. And this umat will be called here in material models, where we have a library. So we will provide and write a library during my tutorials, where today we will begin with a very simple model, which is linear elasticity. So here, if we put linear elasticity in parameters, then we will call this umat, where in general, a given stress T with other internal state variables, all at the beginning of an increment and strain increment, umat updates then T, so the stress, and returns the values at the end of the increment. Moreover, umat calculates a tangential stiffness matrix or Jacobian matrix. The main task of incremental driver is to force the umat to follow a prescribed loading path formulated in stress or strain components. Note that also mixed problems, so combined stress-strain paths, are possible. And for a prescribed stress increment, the components of strain will be determined iteratively in a procedure similar to the equilibrium iterations in the finite element model. Let us now continue with coding the linear elasticity. Linear elasticity, which we'll code, will have only stress and strain state variables, so no other state variables, as for example the void ratio, will be provided. Nevertheless, in the second tutorial, we will continue making it more complex and adding new state variables, as well as hypoelastic stiffness and other models, where at the end the aim is to have rate-dependent models like viscohypoplasticity or viscous elastoplastic models. Let us code here after we defined the characters and the variables. For example, we have the Young's modulus E as real, we have nu, Poisson ratio as real, we have lambda and mu, in which we will code our linear elasticity. The Young's modulus and the Poisson ratio are material parameters which are defined here in resource files in parameters.inp. There we have the name of the model, which is linear elasticity, which again here in materials models it will be searched for real linear elasticity, and if it exists then we will go to this routine, and if it not exists, then the project will give the error and props not correct for will give the error that the material model identifier was not correct. Furthermore, in parameters.it we have two parameters, 2 and props. We have Young's modulus with 30,000 and we have the Poisson ratio with 0.2. Let us continue now with coding our DDS, our model. So first of all, we have to read our parameters, and they are defined as E. So Young's modulus is E, and it was in parameters.inp as props1, so the first parameter, and A nu is Poisson's ratio as parameter 2. Now we have some derived parameters, which are R, lambda, and mu. And I will copy them here. Lambda is E, so Young's modulus multiplied by Poisson ratio divided by 1 plus nu divided by 1 minus 2 nu. Instead of 1 and 2, I could even write 1.0 d0 and 2.0 d0. For mu, we have this relation. And now we have to calculate our tangent stiffness, or Jacobian DDS DDE, which refers to 0. And afterwards, we calculate it component-wise. We could also do a do loop here. And the first component is then lambda plus 2 multiplied by mu, and also the two other components in the diagonal are like that, and the other components read this. So after defining our Jacobian matrix, we can calculate our next stress, which is stress plus DDS DDE multiplied by the increment of strain. So all stress plus stiffness multiplied by strain increment. Now what we want to do is to test our umat. So we implemented very fast a linear elastic umat, and we want to test it now. First of all, we have to prescribe some initial conditions, which here are isotropic. So we have stress in one direction, 2 and 3 as 200 kPa, so negative is compression. And then we have in 1, 2, 1, 3, and 2, 3 components as 0, and we have 0 state variables. So we have defined now our initial conditions. If we would have some state variables, which we will define in the next tutorial, we would have here more lines and also here another number. And in order to run the test, we have to go to this file, test.in. We will begin now with a simple test of triaxial drained test. So the incremental driver will read only until the first and encountered in the test with an asterisk. So it is here. And it will write an output file with this name .out in the file, in the folder where the project is located. And in this case, it will bring up a linear load in 1000 increments with maximum of 30 iterations per increment in 1 second. So here is the time in which the total load will be applied. This time is for our case now not interesting because we have a rate independent model. Nevertheless, in future when we have viscous models, this will become increasingly important. And the next commando is the Cartesian. So we are implying a load in Cartesian coordinates. Therefore, we have here 1, 1, 1, 2, 1, 1, 2, 2, 3, 3. So the main diagonal and the off diagonal components as 1, 2, 1, 3, and 2, 3. If we prescribe in the first number the 0, then we are controlling the strain with this magnitude. If we prescribe a 1, then we are controlling the stress. So we have here mixed conditions with controlling the stress, not changing in the horizontal directions, and in the vertical direction is changing with 15% strain, which is applied with a negative sign. That means compression is negative. If we want to run now this test, we just click on Start, and then we will get this file written out in our folder. So here we have this file that was written out now. There is another possibility to run a drain triaxial test in Incremental Driver, which is maybe more simple than this one, which would be with a prescribed commando, triaxial E strain 1. So in one direction, we apply again 15%. Note that negative is compression, 1000 increments, 30 iterations maximum per increment, and 1 second. We can again run it, and we named it with 2 now. The first simulation one was with 1. Now, how can we see our results? For that, I use Spider and code in Python. You can use Jupyter, you can use anything you want to run my files, where I provide you in GitHub also with 2 plotting files, triaxial CU for undrained and CD for drained. If you drag and drop them here in Spider, now we have here triaxial CD, and we just click on Run, we will see here the first and the second simulation, which of course overlap, because if the commandos are programmed correctly, then they should render the same. And as we see in Q epsilon 1 and epsilon V versus epsilon 1 space, we see that they are just straight lines with an inclination of the stiffness without any plasticity, because we have linear elasticity. Now let us run an undrained triaxial test. The commandos are also written here. Let us first control it via Cartesian. So we have here in Cartesian in 1000 increments, maximum of 30 iterations and 100 seconds. So again, this is not important for our model. We could put 1000 or 1 or 10,000. It would render the same because we have a rate independent model. Nevertheless, for future models with time dependency, it will get important. And we are now controlling Cartesian coordinates, where we control the strains in the 3 directions. And of course, for an undrained triaxial test, we need epsilon V. So the change in volumetric strain has to be 0. And if, as we see here, vertical plus horizontal is 0. So let's run it. It should be an undrained triaxial test with 30% straining in vertical direction in compression. So we run it like this with Cartesian. Let us now run the other possibility, the predefined and pre-programmed commando by Andrzej Niemunis with triaxial U, undrained, E strain, Q in Q direction, where we have again the 30%. Note now that positive sign is compression with this prescribed predefined commando. And we have here again the same seconds, increments, and iterations. And we click again on Start. We'll now have our new simulation here, as we see CU2. We can again plot it with Python, where we see Q epsilon 1 space a straight line with the inclination of stiffness, and QP space we have a vertical line, because of course with linear elasticity we don't have any change in P if so they are uncoupled, and this is what we expected. So that would render me to the end of this tutorial, where we implemented linear elasticity very simply without an additional state variable despite stress and strain. And we run drained and undrained triaxial tests with different variations. So once with Cartesian, just to take a look how it works, if we want to apply arbitrary stress and strain paths. But of course, it is also possible to run it much more faster and simpler if we use the predefined commandos to run a drained and undrained triaxial test. In the next tutorial, we will continue with hypoelasticity and with new state variables, introduction of state variables, as for example, void ratio. And if one wants to take a look how an output file looks like, it is like this. One can open it in an editor where we have time, then strain 1, 2, 3, 4, 5, and 6, and afterwards come the stresses 1, 2, 3, 4, 5, 6. If we would have some state variables, there would follow subsequently after the stresses, which will follow in the next time. Now I wish you happy holidays. I wish you prosperous new year, and let us continue in the new year more with testing of constitutive models in incremental driver, which is not restricted only to soils, but can be used for arbitrary material models and materials. Have nice days.